this. And by the way, I've reloaded and restarted my computer several times so I can actually hear people talk. So don't fear that. But I also have the chat room open here as well. So let me go ahead and share my screen. And move you guys over here. Okay, so again, UV-Vis wasn't in the original thing, but my wife told me that a lot of you do use UV-Vis in research. And so I thought I better go ahead and give an introduction to it, kind of the theory behind it, plus how to actually, okay, that makes sense. And so that you can, get a basic idea of what it's useful for and how to use it, and also give some, you can, actually predict the UV-Vis lambda max for your different compounds that you're making in your lab. So you can do that as a fun thing to do on the side. Okay, so a lot about spectroscopy is dealing with this electromagnetic spectrum, right? So we started with infrared spectroscopy and looking at how that amount of energy could be absorbed by specific bond types and cause them to vibrate. And when they did this, we could actually identify different types of bonds. And then if you put the different types of bonds together, you can start getting an idea about functional group. Then we switched over to the radio frequency band. And in the radio frequency band, we saw that we could take spins of the nuclei aligned in a magnetic field and knock them out of their relaxed state into an excited state. And then we could get additional information about those nuclei and how shielded or unshielded they were by electrons around them. And we could get an idea of position and location and connection. Okay. So now we're going to flip to the other side of the electromagnetic spectrum. And here we're talking about electronic properties. Okay, so we're going to talk about ultraviolet light and how it affects the electronic properties. So we're not going to make the bond vibrate. We're actually going to excite an electron from one bonding orbital to a non-bonding orbital. And the energy difference there tells us a lot about what it is. Okay, so that's where we're going to go on this. So we've been moving around the electromagnetic spectrum with our spectroscopy, but it makes sense to do it. Okay, so if you've never seen a UV-Vis before, it looks something like this. We have a relative thing where we have either percent absorption, or sometimes it's just arbitrary absorbance units. And a lot of times it's arbitrary because, it's affected by concentration, it's affected by a bunch of different things. So you can do it by percentage or just relative or arbitrary, and all of those are fine as long as you can know a little bit more about your molecule. But the keys that we have there also are the wavelength of light. Okay, so this is all in the visible range, but if you go lower in wavelength, below 375 nanometers, we tend to be going into what's the UV. And then the UV will go all the way down to about 150, and then we go to the ultra UV because we have to go into vacuum to actually do UV, because a lot of things absorb in that range. And so we have this band between 375 and practically 200 nanometers to call our UV-Vis area, our UV area. But the visible area goes all the way up to about 700 nanometers, and we can use that entire spectrum to tell us a lot about different parts of the molecule. So, and in this particular case, it's the two types of chlorophyll A and chlorophyll B. And in this right here, what we see is we get this absorption in the red, we get a big absorption in the blue, and it's empty in the green. And because it's not absorbing in the green is reflected back. And that's why green leaves are looking green to us, because that part is not absorbed and is reflected back to us, while the reds and the blues are absorbed. And so that's an interesting factor, is that when things are a color, it's because they're not absorbing that color, not because they are absorbing that color. But that's a whole other course in waves in physics. So we'll stop there. Okay, so another thing we have, because it's concentration dependent and path length dependent, each individual molecule has what we call an extinction coefficient. So it's basically an absorbance related to its path length, and its concentration. Okay, and this extinction coefficient is really useful for us, and I'll show you how to calculate on the next page. The other important thing we'll see in a UV spectrum is what we call the maximum absorption wavelength, or the lambda max. So we're looking at the wavelength that we have a peak in, and that's what we call our lambda max. Okay, and so usually the lambda max is associated with the electronic structure of the compound, and if you change that electronic structure slightly, it'll move up and down based on, it'll either blue shift or red shift, depending on whether you are increasing or decreasing the energy required to make that absorption. And so the position of this is directly correlated to the energy of the absorption. And we'll show you there's an equation for that as well. All right, questions up to now? No? Okay. All right. So like I said before, it was concentration dependent. And so what that gives us is that's exactly how we calculate the extinction coefficient. So what you do is you take your compound right here and you take your UV-Vis spectrum, and then you vary the concentration. Okay. And by varying the concentration, you follow one particular frequency or wavelength right here, and you measure the distance of that and you graph it. And when you graph it, you get the absorbance of the material times the extinction coefficient, the concentration, and the path length. So the concentration is changing, the absorption is changing, and the path length is remaining the same, which means when you graph this here, you should get a slope of a line that correlates to your extinction coefficient. Okay, so that is a very useful tool when you're comparing your molecule to somebody else's molecule, because they might have run it on a different machine with a different path length, with a different concentration. But you can correlate those back and forth by calculating the extinction coefficient and say, oh yeah, that's great. The other cool thing about Lambert-Beer law and the extinction coefficient is you can figure out what concentration of something you have if you know the extinction coefficient and you measure the absorbance. Okay, so that you can back calculate. Like, let's say you wanted to know whether you have, 10 femtomoles or 20 femtomoles of a protein. Well, if you take your UV-Vis and you know the extinction coefficient of your protein in that solvent, you can back calculate to figure out exactly what the concentration of that material is. Okay, so that's really cool. Now, this is also correlated to another rule here, and that's the base 10 log of the intensity measured versus the intensity you're trying to compare it against is equal to a constant times the path length times the concentration. And as we found out, when the extinction coefficient, that constant characteristic of the solute or the compound is the extinction coefficient. Okay, so that we can compare things from 100 years ago to today just by saying, okay, we can just run the calculation and figure out that we do have the exact same compound. Okay, question on Beer's law. So most of the time we just run it at a single concentration, look for lambda max, and then we'll know that we do or do not have that specific compound we're looking for. Okay, so what is doing this absorption? Why are we talking about absorption? Why are we talking about wavelength? Why are we talking about energy? Okay, so if we look at this little equation right here, is that energy is equal to Planck's constant times the frequency. Okay, that's just one of those laws, right? Now we're looking at wavelengths, so if you include the light here, the speed of light here, you can actually get Planck's constant times the speed of light divided by the wavelength is equal to energy. So that means wavelength is directly related to the energy required to do that absorption. Now, if you want to use wave numbers instead, like in IR, the calculation changes a little bit, but that's just wave numbers 1 over wavelength. So, so if absorption is directly related to energy, what is absorbing and why is there an energy barrier between them? Okay, for that, we have to go back to bonding. Okay, so in bonding, when you have two electrons that are in phase with each other, they can get together to form a sigma bond or a pi bond. They can pair up, they can spin couple to get a sigma bond formed. So if we look at this diagram up here, let's say we have a hydrogen atom here, and this hydrogen atom has its electrons in the same phase as the electrons in the next hydrogen atom over. Okay, because they're in the same phase, they can constructively bond together to form our molecular bond or our bonding molecular orbital, our first psi. Okay, and that gives us something like this. And when we have that shape there, we have to think that this cloud right here is the probability that the electrons, the two electrons that are in that bond, are in somewhere in that amount of space. Okay, so it's not an actual shape. The electrons aren't filling that entire space. The electrons aren't everywhere all the time. It's a 95% probability that those electrons are going to be somewhere in that zone. Okay, so now if these are because our electrons are in phase, what if our electrons are out of phase? If our electrons are out of phase, then they cannot constructively bond together, and we form what we call an anti-bonding molecular orbital. And in the case of an anti-bonding molecular orbital, we have the electron density of one far away from the electron density of the other atom because electron-electron repulsion. Because they're not in phase, they can't spin couple, and therefore they repulse each other completely. Okay, and so this is what we call our anti-bonding orbital. And so there's an energy associated, that much higher potential energy in that bond because there's not a constructive build together. So what does that look like? Okay, when we started with our s orbital, our hydrogen had one electron in our 1s orbital right here, and we had a neighboring hydrogen with a 1s electron orbital. When we do that constructive phasing and we can do the spin coupling to create a bonding molecular orbital, that saves us energy. Okay, that's why things bond. We're actually saving energy, having a lower potential energy by doing the bonding. Okay, if we didn't save energy, things wouldn't bond, and this would all be, dust and gases, right? So, but in the creation of this bonding orbital, we've also created a non-bonding orbital. And there's a gap between those two. And that gap between those two takes a certain amount of energy to excite one of those electrons from the bonding orbital into that anti-bonding orbital temporarily before it decays and comes back down. Okay, so now we have our molecular orbitals that are favored, our bonding orbitals. We have our molecular orbitals that are not favored, our anti-bonding orbitals, and the energy difference between them. Okay, so UV, ultraviolet and visible light, is the appropriate energy to be absorbed by these electrons in these orbitals and be excited into that non-bonding orbital. Okay. In IR, it was a lower energy and only caused vibration. This is an electronic effect. It actually moves an electron to a higher excited state. Okay, so that being said, what do these things look like? Well, the one we told you about was this nice little sigma bond. And in that sigma bond that we showed with the hydrogen there, those are the 1s sigma bonds. Now, when we have our 2s sigma bonds, we again form that same kind of spherical electrons to give us our nice stable sigma bond. And our anti-bonding looks exactly the same in the 2s. Okay, now our p's look a little different when they bond. Okay, so if we have a p orbital on one molecule and a p orbital on another molecule, and they are in phase and have a favorable bonding experience, what happens is we gain a large location of where that electron density is going to be in between those two nuclei, but we still have electron density in this other lobe, and we have a node, basically no electron density going through the middle of the nucleus. Okay, so this is just where the electrons can be found 95% of the time. Okay, so that creates a hybridized sigma orbital. So imagine an sp3 hybridized orbital is going to do something like this. Okay. Okay. Now, what if you had unhybridized p orbitals and they were oriented in a way in such that they can do an orbital overlap to give us a pi type bond. What that looks like is, again, they have to be in phase so that they can bond. And then you get a cloud of density above those nuclei, a cloud of density below those nuclei, and those electrons are in either one of those spaces 95% of the time. Okay. But the antibonding orbital, because we cannot overlap this because they're out of phase, they start bending away from each other from that electron-electron repulsion, and therefore you end up with a no electron density here in the middle, and that you still have these orbitals being forced out and not bonding. And then for the next one up, we have, if we have the p orbitals that are trying to make a nice sigma bond, but they are out of phase. Notice this is out of phase with this. What we end up doing is decreasing the size of the lobes that are in between the two nuclei and increasing the size of the lobes that are outside the nuclei because of electron-electron repulsion. And we again have a node, no electron density in between those two nuclei, giving us a bonding orbital. Okay. Each of these configurations is associated with an increase in potential energy. Okay, so what does that look like? Okay, so I'm going to pull this one up. So if we look at a relative energy and the transitions available to us, we start with our sigma bond. And so, oops, we start with our sigma bond here, right here. And to go from a sigma, the next orbital it can overlap with has to be, go to another sigma orbital. It's not going to go to an orbital that is not allowed. So it's a sigma to sigma star transition is what's allowed. And it has a very high energy gap between those two. So the next thing up is a pi orbital. The pi orbital is next in energy up, and it has a great transition that it can go from a pi orbital to another pi star orbital. And notice that gap is smaller than the sigma to sigma star gap. Okay, so it takes more energy to see a sigma to sigma star absorption than it does to see a pi to pi star absorption. Okay. Now we have a couple of what we call forbidden transitions, and this is where we have a non-bonding electron. So imagine a lone pair being excited into a pi orbital or a sigma orbital. Okay, so these tend to be, quote, forbidden, although they are very low in intensity and we do see them. We'll see that they are, they still can be seen, but the most important transitions we're looking for are this pi to pi star, and occasionally some of these pi to non-bondings. Okay, so which groups have these things? Okay, so the sigma to sigma star are found in alkanes because there are no double bonds. So there are no pi bonds, so we have only that transition to us. Unfortunately, this is swapped. These are down here and this is up here, so we'll have to correct that. The pi to pi star transitions we see are in alkenes and alkynes, okay? And we can also see them in some carbonyl compounds as well, okay? So anything with a pi bond can see a pi to pi star transition, okay? Now, the N to sigma transitions are alcohols, ethers, amines, and sulfurs because they all have non-bonding lone pairs. So that's where you're going to see that non-bonding lone pair to a sigma transition. And then carbonyls also have the availability of it has non-bonding electrons on its oxygen, and therefore it can go from a non-bonding to pi transition as well. And so, and this doesn't take very much energy because that's a low gap, but it's not a very likely transition, and therefore it's a very low intensity transition. But it has everything about doing, getting the gap, jumping the gap from one to the other. Okay, questions on that?
So you said that alkene should be above and alcohol should be lower.
The pi to pi star transitions are with alkenes and alkynes.
Yes. So the other, my question is about the other, the description about that things. They also have to switch.
Ask it again, please.
Like the description that is written in front of that things, also high energy but are observable in the UV spectrum. This one and also high energy. These two description has to switch.
This description and this description are correct. It's just the label of alcohols. Think about it. These are the ones, the alcohol and these all have lone pairs. So this name group has to be down here in the non-bonding to sigma transition. Okay. So it's just the name alcohol, ethers, amines, and sulfurs needs to be in the non-bonding to sigma transition. The alkenes and the kynes needs to be up in the pi to pi star transition. Okay. Everything else is right. Okay, it's just this box right here. Oops, sorry. This box. Oops. This box needs to be swapped with this box, and everything else is correct on the slide. Okay. All right. Okay. So now we have our orbitals. We understand which orbitals are contributing to which kind of things, and now we have the idea that there's an energy associated with this gap in orbitals. So what we're going to look for next is putting it all together. So in tables, we typically see the compound we have, what kind of transition we see, what the lambda max is, what the extinction coefficients, and occasionally talk about the different kinds of bands that they are giving rise to those electronics transitions. Okay, so I'm going to blow this up a little bit. So in ethane, we only have sp3 hybridized carbons and hydrogens, and therefore we have no pi cloud, we have no non-bonding electrons. The only available electronic transition is our sigma to sigma star. Okay, and we see that that's a very small wavelength, which is very high in energy. Okay, now once we get to water, we still have sigma bonds, but we have non-bonding electrons on the oxygen. When we have those non-bonding electrons on the oxygen, that's a smaller gap, and therefore we see a higher wavelength, which is a lower energy. Okay, and then methanol, same thing, higher wavelength, lower energy. And then we get to the thiol has lone pairs on it. Halogens have 3 lone pairs on them. So they also have that transition. And we're getting easier and easier to make that transition. Notice that wavelength is getting closer and closer to visible. Visible starts right around 400. So we're getting closer and closer to visible light. Okay. And then our first look at a pi to pi star transition is in ethylene. Okay. Notice that in ethylene here, we also see a big jump in extinction coefficient. Okay, so that pi to pi star transition is number 1 right here at 165. Actually, let me switch colors here so we can look at the pi to pi star transition separately. We change the energy, but we have much higher extinction coefficients. So it is more likely for these compounds to be absorbing at those wavelengths than some of the other compounds. These are very low extinction coefficients. They're very hard to see. Okay. Now, notice that when we add a second pi to acetylene, we actually have a tighter bond there. And so the frequency changes slightly and the extinction coefficient goes down. Okay, now that we go to acetone, you're saying, oh, well, why does it have a pi to pi star transition? Acetone has a carbonyl. The carbonyl has a pi bond, right? It's got a sigma bond to oxygen, a pi bond to oxygen. So it does have that pi to pi transition. It's not just double bonds between carbons or triple bonds between carbons. So we have to think about functional groups like aldehydes, ketones, and carboxylic acids, or things like nitro groups. Nitro groups have oxygen, nitrogen double bonds. And we can see those pi to pi star transitions available to us there. So in acetone, we actually have the pi to pi star, the non-bonding to sigma star, and the non-bonding to pi star. And so the pi to pi star is the highest in energy of this particular one, with the non-bondings to sigma and non-bondings to pi being lower and lower in energy. Now let's look at that diagram again right here. Because the non-bondings are in this middle range, these absorptions are lower in energy than this transition. And we see that in acetone specifically because our pi to pi star transition is at 150 nanometers and our pi to sigma transition is at the 188 nanometers, and our 279 nanometers is where we see our non-bonding electron to pi bond. And that's the lowest energy. However, because this is technically a forbidden transition, it's a very low extinction coefficient. Okay. Now we have our pi to pi transitions. Now, what's the next thing we're going to change? We're going to start linking them together. We're going to start adding conjugation to the system. So in this right here, we're adding carbon-carbon double bonds in conjugation with other carbon-carbon double bonds. And we see a lowering in energy and an increase in the extinction coefficient. And then this is a carbonyl in conjugation with a double bond. And so we see the non-bonding electrons to the pi star transition, but we also see the pi to pi star transitions. Again, this non-bonding to pi is a forbidden transition, is very low absorption, very low extinction coefficient, but the extinction coefficient for the pi to pi is very high. Okay, now I'm going to pull out just a little bit because we've now started into what we call the bands. Okay, by assigning the different bands, it also helps you decide, number one, how strong or weak it's going to be, whether or not the material's in conjugation or not, and what types of interactions you'll see. For example, benzene has a couple different types of interactions, even though it has, you know, it supposedly has, you know, it's not hexatriene, it's not 3 isolated double bonds, and it's not just 3 conjugated double bonds either. It has aromaticity, and aromaticity gives rise to other bands. Okay. Here, hang on. Okay, so the first band we want to talk about is this R, which is basically isolated chromophores, and that's what we call an R band. The K band is our conjugated chromophores, things where more than 2 pi bonds are in conjugation with each other. And then when we get to the E bands, those are ethylenic. So those are like ethylene. However, we have 2 different kinds of those, and I'll define those in a minute. And then we also have benzoid, which are things that only occur in aromatic conjugated systems. So you can have conjugated systems that aren't aromatic and they won't have an absorption in the B band. Okay, so we have different kinds of bands. So that's why when you look at benzene, it has all these different peaks here. We have all these aromatic, and they're all pi to pi star, but they all have different energies and they all have different extinction coefficients because they are given rise for different types of bands. Okay, so let me actually go up a slide and define the bands. Okay, the R bands are typically the sigma to sigma star or the non-bonding to sigma star. Actually, that's supposed to be a sigma. No, it's, yeah, non-bonding to pi star transition. This is for isolated chromophores, and this tends to be a weak forbidden transition. Okay. By forbidden, it means in theory it shouldn't happen because the energy gap is not aligned. There's a better way to say that, but I'm drawing a blank. Sorry. The K band is the more common one, and that's our standard pi to pi star transition in a conjugated chromophore. That can be conjugated with another carbon-carbon double bond or a carbonyl or a carbon-oxygen double bond. Okay. So the B band is found in the pi to pi star in aromatic or heteroaromatics. So this begins our benzoid peak, and so that we only see this band in aromatic rings, and because it's the aromaticity changes the electronic structure. Now, Within that, we tend to have these two other bands. We have this ethanolic and aromatic rings, which is our E1 band. So imagine if the B band is the whole ring acting together, the E band is one of the double bonds acting separately, okay? And it's only that pi to pi star transition, okay? But an E2 is actually a pi to pi star transition in an aromatic system. However, there has to be some non-bonded electrons around there. So things that are substituted with oxygen, nitrogen, sulfur, or heterocycles with a lone pair on them. Those are all things that'll give rise to this E2 band. Okay. So those are the different bands. Now let's go back to the table above and look at the last couple examples here. So
can you explain with an example about E2?
E2, yeah, I can do that right here, actually. If we look at this benzene ring, okay, so if we think about the benzene ring, the E1 band is right here, a pi to pi star transition in an aromatic ring. So just the nature of it being an aromatic ring and having a double bond in it makes that that transition. So imagine an individual pi bond inside the benzene ring is giving rise to that. Okay. So that's the E1 band. Okay. Now notice in benzene, we also have an E2 band and a B band. Okay. Those are the three bands we show here. Okay. The B band is just the fact that it's aromatic. Okay. It's a lower energy, but it's not very high in the structure. I'm sorry, it's not very, doesn't have a high extinction coefficient. Okay, so this next one is a pi to pi star transition, but it's not an isolated pi bond. It's still it's still a carbon-carbon double bond, but it has to be within a pi cloud. So that's the E2 right here. Does that make sense? And notice that the pi cloud, the isolated pi in the cloud has a higher extinction coefficient than the delocalized pi in the cloud versus the actual aromaticity related band. Okay, did that clear it up? Okay. Okay, so now that brings us to our E2 band in other things. For example, in the case of phenol right here, we have our aromatic pi to pi star transition, but we have the phenol. The phenol has a lone pair on it, and that also gives rise to an E2 band, okay, for those non-bonded electrons in the system. Why is that an E2? There are no non-bonded electrons here. I'll have to look that one up.
So why not E1?
It does have an E1 transition, and it's at a different energy.
Okay.
And it has an E2 transition at a lower energy, and it has that aromatic at an even lower energy.
Okay, so you are saying that including the benzene, or it also showing the phenol? I'm telling about the phenol. So
this E2 band is given rise by the fact that it has an atom with non-bonded electrons. And this is just the benzene ring itself.
So why it's not showing the E1?
It might be overlapped with the E2.
Okay.
Sometimes the bonds are close enough in energy, they overlap each other. And we'll see that a lot in a couple other things. Okay. So what we can see is that the different bands give rise to, come from a different place in each of the molecules, but they also give an idea about the energy levels required. And by measuring them and knowing that the wavelength is increasing, that means we know it's a smaller and smaller transition going from the pi to pi star. Okay.
So last question. Yeah. There is a word isolated chromophore. The chromophore, I am confused with this term.
Oh, that's a great lead in because that's on the next page.
Okay.
Okay, a chromophore is any covalently unsaturated group that's responsible for an electronic absorption. Carbon-carbon double bond, carbon-oxygen double bond, the nitrogen-oxygen double bond in the nitro group, okay? So it's anything with a double bond in it and covalently bound. Anything with a double bond in it gives rise to the idea that we can absorb a pi star transition or an end to pi star transition in a wavelength up within the UV-Vis spectrum, okay? So that is what a chromophore is. So just imagine anything that is, you know, conjugated or has a double bond in it can possibly be a chromophore, okay? Now, if we have a chromophore, or if we have a double bond, I'm sorry, if we have a saturated group with lone pairs, like oxygen, nitrogen, when it's attached to or can be electronically related to a chromophore, it will change the absorption. So imagine in that idea, in that example with phenol, we had benzene, it showed up in a certain place. Just by adding the phenol to it, it's going to change the wavelength and intensity of absorption. So the oxochrome is something that will change the core molecule because of its lone pairs. Okay. And then we have what we call bathochromic. And bathochromic means that if you substitute something or change the solvent and the color and the energy level goes down, we tend to call it red shifted. So it's bathochromic, it's shifting to the red, it's shifting to lower energy light. So that means there's a cooperative effect with the solvent or the substituent that lowers the energy of the transition. In contrast to that, you have a hypsochromic effect, which means that it increases the energy required to make that transition with either a substitution or a solvent. So it's actually hurting the transitions, making that transition gap bigger, and therefore requiring more energy to make that transition. Okay. Now, then there's the last two here are hyperchromic effect, which is something that increases the absorption intensity. For example, multiple conjugations tends to be hyperchromic. It increases your absorption intensity. But then there's also hypochromic, which means you can decrease absorption intensity. And these effects are also found in solvents. Certain solvents can minimize, increase, or decrease. For example, if a solvent hydrogen bonds strongly to something, that can take away some of the effect and actually decrease the absorption intensity. Okay, so now do we understand chromophore? All right. Okay, so the next thing we want to do is talk about sample prep. So obviously concentration is important and path length is important. So most of the time what we see is we get our cuvettes that we use in there, and they're exactly 1 centimeter wide. Okay, now that's not to say that that's always true. Sometimes you'll see them where they neck down in the middle and they'll have narrower and narrower gaps, but they all have fixed gaps. Okay, so you can have 1 centimeter, half centimeter, and if you have very little solution, you can actually put a thin film inside a cuvette. As long as you know the wavelength, you can back calculate out your absorption, absolute absorption, and your extinction coefficient. Okay. So that being said, your molecule has to be dissolved in a solvent. You have to be able to change the concentration to know that to measure your extinction coefficient. So you have to dissolve in a solvent. So what you look for in an IR solvent, the UV-Vis solvent, is something that does not absorb in your area of interest. Okay. So let's say you have something that is like acetone or something like that, that it actually absorbs way down in the 150 range. So that's the way you won't see any of it there. But good solvents, water can be a very good solvent. It actually starts having a tail absorbing a little over 200 nanometers, but a lot of your biochemistry work is done in that water. And then you can also use methanol, ethanol. They have minor absorptions. And acetonitrile is almost transparent across this entire range of 200 to 400 nanometers. Okay, So solvent choice is a big choice. And because some things can be bathochromic or hypochromic, you have to know if your solvent is going to change your lambda max. So sometimes you can run something in chloroform and you'll get one lambda max. You run it again in cyclohexane and you get a different lambda max. And that has everything to do with the solvent effect. Okay, so that has to be written down and understood in your system, that you try to use the same solvent all the time. Okay. Or when you do change solvents, you know that it doesn't have an effect on your system. Okay. So let's just start talking about different classes of compounds. So the first thing we want to talk about is saturated systems. In saturated systems, the only transitions we tend to have are our non-bonding pairs to our sigma. Okay, now, why didn't I say sigma to sigma? Because that's a very high energy transition, and it's typically out of the range. It's typically in the 120 nanometer range, and that's outside the range of what we normally see in our UV-Vis devices. We're starting to get into the vacuum UV. So because that's in the vacuum UV, we tend to start with only the non-bonding to sigma transition. And that's things like methanol, thiols, ethers, alkyl halides. These all start to see absorptions from that non-bonding electron to the sigma orbital, non-bonding orbital. Okay. Now also,
so it's mean we can't see absorption for alkanes.
Correct, because the alkane absorption is going to be so low. It's like 125 nanometers. We can't measure it in a solvent-based system.
So if there is a functional group in the alkane, then we can measure it. We can use
Correct.
UV. Otherwise, we can't use it.
Notice all of these have non-bonding electrons. They all have lone pairs. Oxygen has 2 lone pairs. Thiols have 2 lone pairs. Halides have 3 lone pairs. So anything with a lone pair, you can see the non-bonding to sigma transition. Okay? So it's really not useful for alkanes. And so that makes alkanes a great solvent to use in UV-Vis, because they don't absorb in the entire range. Okay. Now notice that this methanol here starts absorbing. It has a lambda max at 177. Okay, so that means that's its lambda max, but it still has a tail on it. So that's why when we look at our solvent here, methanol actually has the useful range start up here at around 210. And the reason that, that it has this useful range starting at 310, because its lambda max is 177 right here, but it still has that tail, and that tail will affect the operating window of your solvent. Okay, so in general, most of these make really good solvents unless they start absorbing above 200. Okay, so we like to see methanol as a solvent and ethanol as a solvent and diethyl ether as a solvent too. Okay, but some of the other ones, like these sulfides, are starting to absorb in the 200s. They become poor solvents for the system. Okay, so that's the saturated system. So they're not really that useful to do a UV-Vis on the saturated systems. What we mostly do is do it in our unsaturated systems. So when we start with our unsaturated systems, here, let me go turn the fan on. It's getting warm in here. Okay, all right. When we talk about our unsaturated systems, the first kind of unsaturated system we have is what we call isolated, meaning that it's just a single chromophore, a single pi bond somewhere in the molecule by itself. Okay, so we think of things like ethylene or acetylene or a ketone or an aldehyde. These are all things that are only that double bond is doing the absorption in the UV-Vis. Okay, So if we think about it there, these are, in ethylene, we only have our pi to pi star transition right here. And it has a couple different absorptions. It has our higher energy absorption and lower energy absorption, depending on what the groups are here. And then our acetylene has an intermediate one there as well as our Electromagnetics. Our carbonyl compound and acetones have two. Because we now have those non-bonded electrons on our oxygen, we now have the opportunity for our non-bonding to pi transition. So we actually see two different transitions at two different wavelengths. Okay. Aldehydes typically only have the one right here, the non-bonding to pi. And notice these non-bonding to pi, because they're, quote, forbidden transitions, they are very low in intensity. Okay. So carboxylic acids, you might not think of that, but it has a carbonyl in it, and so it does actually have an absorption there. And it has a pi to pi star transition. I'm sorry, an N to pi star transition. And then anything with a double bond, this carbon, nitrogen, azomethane has an absorption with the pi to pi star. This nitroso group has a pi to pi, actually that has a pi to pi star transition and an N to pi star transition. This is the N because it's the lower intensity one. Nitro group here has that shared double bond, so we get that absorption. Sulfur groups with double bonds to oxygen also have those absorptions. Now these are all what we call isolated chromophores because that is just that one double bond is doing all the absorption and there's no other contributor. Okay. And so that's kind of useful for figuring out functional groups sometimes, but IR usually tells you that. So where it really comes into play is where you have the unsaturated conjugated systems. Okay. So imagine getting, the simplest of them would be butadiene. You have two double bonds separated by a sigma bond, and now we see a nice, decent pi to pi star transition and a really good absorption coefficient, extinction coefficient. Our extinction coefficients on these conjugated alkenes tend to be very high. Okay, and when we go to hexatrienes, we get a big, huge boost in shifting to lower energy and really high extinction coefficients. And then by putting them in rings, it changes it a little bit. The intensity goes down, but the energy is still intermediate with the isolated, with the butadienes and the trienes. So conjugation is lowering that transition. Okay. And we see that in all these things. So going from ethylene to butadiene, we see that 50 nanometer change. So that's a decrease in energy. Going to hexatriene, it goes down again. That's an even lower energy. And if we extend that out even further to beta carotene or lycopene. Now in lycopene, what we have to note is that it's only these 11 in the middle that are conjugated. These are isolated. So those would give a separate band. But the 11 in the middle give rise to this 471. So it keeps going down and down and down in energy, or up and up and up in wavelength. Okay, why? It has everything to do with the idea that as you add more and more of these pi transitions, the energy difference between the pi and the pi star gets lower and lower and lower. And in physics, we call that a band gap. So it's the gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, or HOMO and LUMO. So if it's isolated here, our gap is actually pretty high. And at this right here, and we can calculate that energy as a greater than over here. So just by adding that second one, we've now have two pi's that are not in equal energy. They're actually both at different energy levels, and therefore the gap between the pi star, notice the gap between this pi and that pi is the same, and this pi and that pi is the same. But we can go from the higher pi orbital to the lower pi orbital, and it decreases the gap necessary to increase that. Same thing happened here. The gap between the first orbital here, the second orbital here, and the third orbital here, notice those gaps themselves do not change. But we can now transition from this third pi orbital, this third pi orbital, to this first pi orbital, and it has a smaller gap. So increasing your conjugation decreases the energy required to take it to the first unoccupied molecular orbital. Okay, questions on that? This is most relevant for Emma and Marvin because this is conjugated materials this is your whole band theory associated with that. So, all right. So the cool thing is that there's been some rules laid out where we can actually calculate or predict the lambda max and the extinction coefficient based on what we have. Okay. So there's two different ways to do it. Most of the time you just start with this equation here. And in this equation here, if you don't have a ring, you can start with a base value of 114 nanometers, okay? Then you have the number of alkyl substituents times 5, and then the number of double bonds in conjugation, okay? So in lycopene up here, it has 13 double bonds, but only 11 of them are in conjugation. So we'd only use the number 11 there. And so, and then these are fudge factors that he actually derived this equation by looking at a whole bunch of data. And that's what these fudge factors ended up being. And then this fudge factor for the number of rings with endocyclic double bonds and the number of rings with exocyclic double bonds. So in straight chains, you actually end up with zeros for those numbers. However, in the fact of a multi-cycled system, if you have fused rings, you have to use a different starting base. You don't use the 114, you use a 214 or a 235. You use the 214 if it's a trans-like double bond in the ring system, or a cis-like double bond, you use the higher number. Okay. Now, what does all that mean? Okay. Well, the first thing we ought to do is we got to look at what is that. Let's see that. So an exocyclic double bond is a double bond that terminates into a ring. An endocyclic double bond is one that doesn't have that double bond terminate into a ring. Okay, so I'm going to compare and contrast the two different types of cholesterol dienes and show you what I mean by that. So using that equation above, in this system, these are the two double bonds that are in conjugation. And they are a cis-like double bond. So we have to start with, I'm sorry, they are trans-like. So we have to start with the 214 nanometers as our base. Okay. Then the number of ring residue, 5 times the number of substituents added. So there are 3 substituents added to these double bonds. Okay. So let me circle those. This is an R group on a double bond. This is an R group on the double bond. This is an R group on the double bond. So that's 3 times 5, which gives a total number of 15. That's from our equation here. Oops. So our equation says 3 times the number of substituents plus n times this number minus 1 over 1.7 times n. N is the number of bonds in conjugation. For this particular example, we have that number as 2 right here. And then we have 1 exocyclic double bond. So this one, let me circle it in green. This is our exocyclic because the double bond terminates into a ring. This is endocyclic right here. The exocyclic is the one that terminates into the ring, and therefore we add for that. And so by calculation, our lambda max should be approximately 234 is our predicted number. Our observed number is 235. So that's pretty good, plus or minus, right? It's not bad. And our extinction coefficient right here from the equation here is this number times the number of double bonds that are in conjugation. So it'd be 2 times that number. And the predicted number is actually pretty close to our extinction coefficient. Okay, so now let's do one with an endo with the cis-like system. So we have our cis-like system, so it changes our base value to 253. Okay, again, if this was a straight chain linear, we'd start with that 214. I'm sorry, 114. We have 1, 2, 3 R groups attached to our double bonds. So that's 3 times 5, which gives us 15. And we still have 1 exocyclic ring here, which gives our predicted 273. And it gives us our number at 275 as our measured number. So that's pretty close. Our extinction coefficient is a little off, but it gives you a good idea on where to start with, okay? So let's do a linear one. Okay, is the greater conjugation the sense of greater total energy that can push the smaller homolomo transition? Slide 10. Let me see. I have a, is the greater conjugation, it's not necessarily greater total energy. What you can think of it as, though, is that these energy levels are associated with potential energy, right? So this potential energy increases as you go up. So yes, this has a higher potential energy than this system over here because it's higher in potential energy. So yes, it does technically have a greater total energy, and that, but the reason here is that the absolute gap between this one and this one is the same as this one and this one. It's just that now, because this started at a lower potential energy and this is at a higher potential energy, it gives it a smaller total gap.
So I'm a little confused too. The pi 1 is for the first double bond, pi 2 is for the second double bond, and pi 3 is the third double bond.
It's not. It's probably the one in the middle is the lowest energy, and the 2 on the ends are the higher energy. This is just a relative scale. Yeah, this is just a relative.
Like usually it's when the double bond there is 1 pi bond and the other point, but you are showing 3 pi bond, so it's because of 3 double bond.
Yeah, so it's just saying that the these each energy levels are not assigned to each of these double bonds. Okay. And gaps really aren't that big. It's like, if you can imagine, it'd be like they'd be like kind of almost stacked on top of each other here. But the fact is that these are still getting smaller. The gap here is getting smaller. It's a relative term. These are much closer together than they look. And it has to do with, let's say that when, you have free rotation, this could flip around and be cis to the other one, and that'll be a slightly higher energy or lower energy. I don't want to assign individual double bonds to those individual energy levels, though. Okay, so it's kind of a net. It's the molecule as a whole giving rise to these energy levels, not individual energy levels within the molecule. Okay. All right, so let's go and do a straight chain one. And if we do our straight chain one, we of course start with a different base. It's the 114. We have a total of, let's see, how many carbons do we have here attached to double bond? Okay, first of all, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of those double bonds in conjugation. The other two are not in there, so we don't count them. We have 1 R group, 2 R groups, 3 R groups, 4 R groups, 5 R groups, 6 R groups, 7 R groups, 8 R groups. So that means our M is R groups, and so that's 5 times 8. We have a total of 11 double bonds in conjugation. We have no endos or exos because we don't have a ring, which gives our calculated number 474. Notice where we're getting most of this increase in the value from. We're getting most of the increase in the value from N here. The more conjugated units you have in, the higher the number is. The higher the number is, the lower energy that transition is. Okay. Does that make sense? So if you had a molecule and you had a weird anomalous reading and you tried it in 2 different solvents, you could go back, calculate, and see which one is giving you the blue shift or red shift that you're seeing in your molecule.
So
okay.
why we haven't used the equation for the previous example?
This is the exact same equation, except this has rings. Because of the rings, we have to use these ring system. These are our ring bases. This number is only for straight chains. These numbers are for rings.
Yeah, I was thinking that we just have to replace this thing, but we have to use all the other values as well.
Yeah, no, all the other values are in this equation as well as
like the n into 48.0 minus 1.7, and we are not using in this equation.
Okay, yeah, we're using these, sorry. Yeah, this is for rings, sorry, this is for rings because we have the double bond. This is for having the 5s for the number of things you have, and then exocyclic double bond was the other 5. I'm sorry, it is a different equation.
Yeah.
So this is just the 3 things: the base molecule, the number of connections, and whether or not you have an exocyclic or not. Sorry, you are correct. So this one actually uses all the factors in it. Okay, so we're going to extend this now to triple bonds. Okay, triple bonds do that exact same conjugation. In fact, it shows up very favorably for this pi to pi star transition. If we look at hexadiene right here is hexadiene. We see a lambda max at 227, but a very low extinction coefficient for that. We have for that wavelength there. But notice we have 2 different wavelengths here, so it gives rise to 2 different types of absorption. When we get to the octatriene, we end up with a total of 2 right here. One is a very low energy, low extinction coefficient, but one has a very high extinction coefficient. Look at this, 135,000. Okay, and when we extend that conjugation even more, we see a decrease in an increase in the wavelength and an increase in the lambda max. This must be one of the other transitions. This is the pi to pi star transition. This must be another transition because of the low extinction coefficient. I'm not sure. I'll have to look that up. Okay, so we've done it with alkenes. We've done it with alkynes. So let's look at carbonyls as chromophores. Okay, if they're isolated, you only have that non-bonding to pi transition. Okay, because the non-bonding to sigma is too high and the sigma to sigma is too high. So just having a carbonyl in a compound like a ketone gives rise to that non-bonding to pi transition. And remember that non-bonding is above the energy of the pi orbital, so it's actually a smaller gap to go from the non-bonding to the pi. Okay. But again, it is a very low energy absorption. However, it has a very low extinction coefficient. So if we look at acetone here, we're actually getting really close to 300 but here, but it's very small extinction coefficient. Okay, so as our ketones are all, this entire group of ketones are all right in the same range, and none of them have a very high extinction coefficient. However, okay, yeah, and so then those are all ketones. If we go to aldehydes, carboxylic acids, esters, and amides and acid chlorides here, again, we're looking at that carbonyl function of all those different derivatives. And excuse me, we'll see that they again are all that N to pi star transition, so they all have very small extinction coefficients. Okay, so that's if they're isolated. If they're isolated, we only have that non-bonding to pi transition. What if they're conjugated? If they're conjugated, now things get really interesting because our extinction coefficients will go up for our pi to pi star transitions. Okay, so if we look at some simple ones like this, just by adding a carbon-carbon double bond in conjugation with this ketone here, we see, excuse me, a K band. And if you'll remember what the K band is, the K band is that pi to pi star transition. The R band is the N to pi star transition. So let's go back. Okay. I'm going to have to stop here. My stomach is not feeling very good, and so I'd like to go ahead and pick up on this on Thursday, please. Okay, so I'm going to go ahead and stop sharing and start recording, and I will see you on Thursday.